Thank you, and thanks so much everybody for coming today. It's my great pleasure to present our work on continuous variable quantum designs. Here's a rough outline of my talk today. So there is some nice mathematics in this work, but since I only have 20 minutes with you today, I'll really just be trying to convey a few high-level messages, some take-home messages. The first being that we've extended the notion of designs to infinite dimensions. We've constructed a few examples and we've shown some applications. The main message is really that designs are sort of used all over the place in finite dimensional quantum information theory and experiment. And given our work, we believe that some of these applications are sort of ripe for the picking, so to speak, to try to extend to infinite dimensions. So that's really sort of what I'd like to get across. And so why infinite dimensions in the first place? I mean, continuous variable quantum systems are in many ways quite different from their finite dimensional counterparts. It's sort of not as simple as thinking of an infinity by infinity matrix. There's some situations in which really there's things you can do in infinite dimensions that you just cannot do in finite dimensions. I encourage you to take a look at this review here that I've cited in blue for some more information on that. But since many of us are more familiar with finite dimensional systems, let me just draw a few very rough analogies just to get an idea. I won't talk about all of these, but let me just go like one at a time through a couple of these. So in finite dimensions, we have qubits, which are d-dimensional quantum systems. In infinite dimensions, we have oscillators. Stabilizer states in finite dimensions correspond to roughly two Gaussian states. These are states with the quasi-probability distributions being Gaussians in phase space. The Clifford group is sort of roughly analogous to Gaussian unitaries, which Ludovico just talked about before. And then the one I want to draw your attention to is this one down here. So the set of all stabilizer states in many dimensions, although not all, but in many dimensions, they form a quantum state 2 design. And similarly, the Clifford group oftentimes forms a unitary 2 design. This sort of analogous result does not hold in infinite dimensions. So there's this work in 2011 by Bloom, Kohout, and Peter Turner. And they show that Gaussian states do not form a 2 design in infinite dimensions, a continuous variable 2 design. And indeed, by extension, Gaussian unitaries don't form a unitary design. And this is really the start of our work here. So I've said design like 30 times. I haven't yet said what it is. So let me give a sort of rough definition of what a design is. So consider, for example, just this orange triangle here on the right and just a subset of 2-dimensional Euclidean space. And then we can focus on these like 3 points sort of on the edges of this triangle. And what you can show, very easily by direct calculation is that if you perform an integral of an arbitrary degree 2 function in polynomial in x and y, if you integrate over the orange triangle, it's exactly equal to if you just sum over the evaluations of the points at these on the 3 edges. And so we would say that this set D here is a 2 design for this triangle. And this is really what a design is it's taking an integral over a hard space and it's reducing it to an integral over an easier space. In this case, that integral was just a sum. And this reduction is exact whenever the function classes that you're interested in are just degree t polynomials or less, degree t minus 1, etc. So this is what a polynomial is, but we can consider, this is not what a polynomial is. You can consider much more general spaces than just this orange triangle. So for example, if you let x was a triangle on the previous page. If you let x be a sphere, these are like spherical designs. If it's a unitary group, they're unitary designs. If it's complex projective space, these are quantum state designs, QIP designs, where, this is the set of all quantum d-dimensional quantum states. Again, I won't go through all these. Designs are kind of everywhere in some way or another. Let me just point your attention to 2. So unitary designs are used a lot in randomized benchmarking and elsewhere. And unitary and state designs are used in state tomography, and I will sort of come back to these 2 examples, but these are what we'll focus on. So for us, a very intuitive way for us to visualize quantum states will be in this picture on the right. So as an example, just consider a qubit. You can imagine we have the 2 simplex here, which is the set of all probability distributions on 3 elements. And we have a torus here, a bunch of Cartesian products of circles. And a point on the simplex and then a point on the torus corresponds to a quantum state, a qubit state. And this generalizes obviously to higher dimensions. it's not a one-to-one parameterization, but it's a useful parameterization. And so, right, so we can move this point around, and it gives you a different probability distribution over the basis states, and then you can move the phases around on your torus, and it gives you different phases. And then this point right here in the center, the centroid, is the uniform probability distribution, and this is sort of an important point for us in our talk, in our work. So again, some nice intuition is that if you take a quantum state design, you can project it down to the simplex via the Born rule, essentially, and it gives you a simplex design. And similarly, you can take a simplex design and a torus design, and you can sort of combine them to give you a quantum state design. Now we can try to generalize these ideas to infinite dimensions. So there's this sort of catch-all work by Seymour and Zlotowski in 1984 that shows that basically for any well-behaved space that you can think of, T designs exist. And then, as I mentioned before, the Clifford group forms a unitary 2 design for many dimensions, and indeed sometimes forms a 3 design. But then again, there's this sort of work from before that shows that Gaussian states do not form continuous variable state 2 designs. And by implication, Gaussian unitaries also don't form unitary 2 designs. And they sort of leave as an open question, can we find 2 designs and higher in continuous variable systems? And this is the first main result of our work, is we show that you can't. There's no ensemble of continuous variable quantum states that you can use to generate a quantum state 2 design, or higher, for any t greater than or equal to 2. And then again, by extension, this implies that you can't have a continuous variable unitary t design for any t greater than or equal to 2. So my first message that I told you in the beginning was that we constructed designs. So I'm somewhat contradicting myself, but I'll hopefully describe that. So let me just give some rough intuition for how this theorem is, sort of intuition for why this theorem is true. As I mentioned, in finite dimensions, you can project a design down to the simplex, and it yields a simplex design. And this holds over in infinite dimensions. And what we show, very, very roughly, is that any simplex t design for t greater than or equal to 2 requires a point which is very close to the centroid, which is the uniform probability distribution. This uniform probability distribution here. And as you go to infinite dimensions, there's no longer a notion of a uniform probability distribution on infinitely many elements, because you just zero out. And so this is sort of how we prove a contradiction. Much more formally, we sort of use measure theory and functional analysis and to derive this contradiction. But as I said, we do develop a notion of continuous variable designs, and so we want to get around this, and we see that it's really this normalization condition of probability distributions that's kind of preventing us from having designs. So we naturally just take away this condition. We say, well, let's just not require states to be normalizable. So consider an infinite dimensional Hilbert space. We might as well consider L2 of R. Our results hold generally for any separable Hilbert space, because they're all isomorphic to this guy. And then let's just fix some countable basis. Some examples of non-normalizable states on this space are position states, for example, the ket x state or momentum states, ket p states, and there's GKP states and phase states. These are all non-normalizable. They're not square integrable wave functions. But in many situations, although not all, but in many situations, you can still make sense of them by going to something called the rigged Hilbert space, which I won't talk about, but it is a way to formalize these sort of objects. And so we can sort of do the same thing, and we just remove normalization. So, for example, here is a rigged 2 design. So we call it a rigged T design because it utilizes the rigged Hilbert space. So they have these basis states here, and then the design also consists of these phase states, which you notice is a uniform superposition over all basis states, and then there's some phases here. Again, just to emphasize, this is not normalizable clearly. However, it is a so-called tempered distribution. It lives in this rigged Hilbert space, and so we'll spend the next few slides making sense of it. But we notice that this essentially gives us a notion of a non-normalizable centroid. So let me just go through a couple of applications. So the first one will just be shadow tomography. So in finite dimensions, you can generate so-called qubit shadows. And these qubit shadows are very good approximations to your quantum state when you want to, for example, estimate expectation values of many observables. And most shadow tomography protocols utilize designs because they give you good guarantees. And indeed, you can sort of just take our rigged T designs and port them over, and you get very similar guarantees. You get different types of shadows. Now, one question that obviously sort of pops up is, well, what's going on here? Because this is not a quantum, like this is infinite dimensional. Like, how can you do this with non-normalizable states? And the reason is really because these non-normalizable states don't make sense as states on their own, but they do make sense as POVMs. So a rigged 1 design is a POVM, and a rigged 2 design is a POVM plus a little bit more, and etc. So you can still measure with respect to these rigged T designs. And by performing this measurement, you can then store results classically, and it doesn't matter that they're non-normalizable because you're just storing them classically, and then you can just do the full procedure. And so, for example, this is sort of like a very analogous result that you get in finite dimensions. I won't really go into the details of it, but if you want to estimate the expectation value of a large number of observables, you only need to sample, logarithmically many times from your state. And okay, this function f here is like some function like a trace of the observable squared or something like this. G is slightly more complicated, depends on the state, but for many states it's still okay. And indeed, like as you go to higher T, you sort of get better results. And one thing I want to mention, and I will mention a little bit more at the end, is that this is not the only way you can do continuous variable shadow tomography. There are at least 2 proposals that I know of. One of them by the previous speaker, Ludovico, and one of them by Shrilanka Gandhari and Victor Albert and Michael Gullans. And I'll come back to this at the end. Okay, now we'll go on to the second application, which is for average fidelity, entanglement fidelities, generalizing these ideas to infinite dimensions. To start, though, we'll sort of talk about what we call regularized rig designs. So as I mentioned, these rig designs have non-normalizable quantum states, but sometimes you want to have physical states in your design. And so we do this by introducing a regularizer, R, which just it takes your non-normalizable state and normalizes it and makes it into a valid quantum state in L2 of R. And so, for example, if R is a projector onto, say, like a low energy subspace of your Hilbert space, we would call this like a hard energy cutoff. And then in that case, taking a rig design and projecting and regularizing it with this R just gives you a finite dimensional design, as you would expect. But more generally, you can choose an R that maintains support on all of the Hilbert space. So this would be like an invertible regularizer. And it needs to be trace class, so it'll decay as you sort of go up in energy, but nonetheless, you're still invertible. And so in this case, for example, you can take the phase states that I showed in the previous slide, and you just regularize it with R, and you get some exponentially decaying factor. Okay, so we're going to use these now for average fidelity and entanglement fidelity. So let me just tell you briefly what average fidelity is. So very roughly, the average fidelity of a channel, of a quantum channel E, is sort of how close that channel is to performing just the identity channel on average. So it's not a worst case, it's an average case. And the entanglement fidelity is like how well does your channel preserve entanglement. So in finite dimensions, we usually take this average here, this average over states D, to just be all quantum states. You can just average over all quantum states, but completely equivalently, you can just average over a 2 design because you only have 2 factors of the state there. And then psi is like a maximally entangled state, and then there's this beautiful relationship by Horodecki, that relates the average fidelity and the entanglement fidelity. And it just has this very simple, nice form. Now in infinite dimensions, we do sort of analogous things, but with our designs. So now we average over all regularized rigged 2 designs, and then we let phi be something very analogous to maximally entangled state. It's like a maximally entangled, like a non-normalizable maximal entangled state, normalized or regularized by our regularizer R, which for many regularizers this is just like a 2-mode squeezed vacuum state. And then whenever R is invertible, so whenever it maintains support on the full Hilbert space, you get this exactly analogous relationship, but the dimension factor is now replaced by some sort of effective dimension, which depends on how you're regularizing your space. And I emphasize that this only works when R is invertible. When R is not invertible, you get some extra annoying factors. However, if R is not invertible, and for example, if R is a projector like this onto a finite dimensional subspace, if the channel that you're dealing with only acts non-trivially in that finite dimensional subspace, then you reproduce this left-hand side, which is what you would expect. But more generally, right, we have more general regularizers, and then you get this nice result. And this dimension factor in this particular case here is related to the average Fock state number in the thermal state. Okay, great. So let me just tell you a quick summary. So we showed that continuous variable state and unitary t designs don't exist for any t greater than or equal to 2. And really the reason that they don't exist is because we need to make our states normalizable. And so to get around this, we formally go to the rigged Hilbert space, we use so-called tempered distributions, etc., and we generate these rigged designs. And since rigged designs are POVMs plus a little bit more, this allows for things such as shadow tomography. And then you can apply regularized rigged designs to get sort of physical states, and then that allows for nice notions of average fidelity that sort of match very analogous results in finite dimensions. So now this is, as I told you in the beginning, my main message that I would like to get across is that there's sort of lots to do. So this is sort of some of these things. So, okay, one thing is just find more rigged designs, in particular rigged designs that play nicely with experiment, with like actually measuring these things. Indeed, the phase state design that I showed has, there's some papers about trying to sort of measure with respect to these POVMs. It's been an open problem for a number of years, and so it would be very interesting to sort of have some proposals for that. All right, so for the shadow tomography, in finite dimensions, there's a lot of sort of optimality arguments that, as far as I understand it, sort of use the notion of designs to make some of these optimality arguments. And so it's an open question, like with our design-based shadow tomography technique, is can we extend some of these optimality arguments to the continuous variable regime? Next, I talked to you only today about continuous variable state designs, but using the notion of state designs, you can define unitary designs exactly analogously. And in many procedures in finite dimensional quantum information theory, unitary designs are sort of crucial. So one example is like randomized benchmarking. Typically, state designs are not enough. And so it's an open question to try to find some of these unitary designs and see if we can extend sort of finite dimensional things to finite dimensional protocols to infinite dimensions using these designs. And indeed, more than just benchmarking, really anything, as I said, designs are really used in many, many places, including state designs in finite dimensions. We've sort of extended 2 such use cases to infinite dimensions, and hopefully other people extend many more. So thank you. Here's my wonderful collaborators. I appreciate your attention.
Okay, so many thanks for interesting talk. I would have 2 questions. First of all, about, there are those 2 examples of very celebrated T designs, MUBs, the full sets of mutually unbiased bases, and the SIG POVMs. Do you expect to find the rigged equivalents of those?
I have thought about this for so long. Yes, so I hope so. I don't really know what else to say. It's weird. It's like we're close. The rig 2 design that we have is sort of, it's like a MUB, but it's like slightly not because of some, yeah. We can talk about it more after. Hopefully you have ideas.
Thank you. And one more question for me, because I didn't get this thing about point close to the centroid in the simplex designs. Because as far as I know, at least in the 2-dimensional MUB, you can rotate it in such a way that none of the projections is close to the center of the probability simplex. So I'm not sure if I understood how it's really necessary to have this point.
Yeah, yes, it's very sort of rough intuition. Right. More formally, it's really just a measure theory proof. You don't have to, I say close to the centroid, I really mean like anywhere not on the boundary. This is really sort of what I mean there. Thanks.
Yeah, also thanks from my side. I must have missed a technical detail. So why do you not consider the full state space as a T design? Why is that not allowed? You say there are no T designs. Why is this not a T design?
Like all of the Hilbert space? Yeah. There's no
You want it to be finite in some sense, or smaller, or?
Yeah, so you can't put there's no good measure to put on an infinite dimensional Hilbert space that will reproduce a design. You can put measures on an infinite dimensional separable Hilbert space, like a Gaussian measure, but it won't give you. It'll actually give you a regularized rig design. It won't give you. It won't actually reproduce. A good thing to look up is to like go into Wikipedia and look up non-existence of Lebesgue measure in infinite dimensional Banach spaces.
Okay, thank you.
I'm happy to chat more also after that.
Hey, thank you for the great talk on continuous variable. One of the experiments I work on is like using like the Schmidt number basis, right, for QKD, like the frequency time binning, right? So can you give a quick pitch about why I should switch to CV instead?
That's a lot of pressure right on the spot. I will say refer to the review on the first page. This guy right here is standing up there. He knows a lot about continuous variable. And he will answer the question way better than I can hope to. And you'll have to pitch yourself to him as well. And there he goes. Bye. He's nice, I promise.
Thanks for the nice talk. I was wondering, in finite dimensions, we have this great tool of frame potentials to check whether something given is a design. Is there anything similar in CV?
Yes, in our paper we have frame potential for regularized rig designs. The analogous thing sort of doesn't really hold for rig designs because a frame potential you usually you sandwich states together, and when you take non-normalizable states and sandwich them, you get infinity, right? So, but it works for regularized rig designs. So there's some very completely analogous formula with these R's put in there in some places, and right, but yeah, exactly analogous. Great question.
You said you were gonna compare with other approaches to shadow tomography in CV systems.
Did I not mention it? Maybe not. Yeah. I guess I didn't mean compare. I guess I meant I wanted to emphasize that this is not the only way to do shadow tomography in continuous variable systems. I wanted to make sure I wasn't saying that we were the only ones doing shadow tomography. Yeah, really, it's a question of, like I said, hopefully maybe we can extend some optimality arguments to infinite dimensions with design-based techniques. Maybe not. That's an open question. Experimentally, the other protocols are almost definitely better. But again, maybe our friend here can prepare these measurements in his lab once he switches to continuous variable.
Hi. So you mentioned as one of your open problems constructing infinite dimensional unitary designs with the appropriate adjectives. Is it also an open problem as to whether they exist, or is it now known that they exist and you just have to make them?
Yeah, I'm actually not willing to say whether or not I think they exist or not. I think they exist, but I don't know. Yeah, I don't know. I think I would suspect that they do, but I don't know. Hopefully they do. Maybe you can tell me one day.
Thank you for a nice talk. So you mentioned that pure Gaussian states, they do not form exact two design in infinite dimensional case. So what if you regularize, if you take those cutoffs, do they form then those regularized two designs?
That's a great question. I don't know. That's a very good question. Yeah.
Thanks.
I presume there might be some sort of measure that you can put on the space of Gaussian states. Yeah. Right. Yeah. That's a great question. Thank you.
Okay, before we thank Joseph, just a few announcements. One is that the coffee break is going to be at the UFO now, and after there's the business session and the industrial session, and then there's the dinner, which is at 7, and the location is in the program. So let's thank Joseph and all the speakers of the session.